mostly I have the script in case all the technology fails and I've still got the content of the slides. But it's useful sometimes to remind me of things. So it's my fault you have this meeting because I helped to arrange it. You'll find that some slides will contain information which I'm actually going to gloss over fairly quickly. And that's because I'm used to talking to students who don't buy textbooks, mainly because they can't afford them. And so students want as much as possible to be on the slides. And so I put more on than I need sometimes. The slides will be on the website, and you can see the website address at the bottom there, and that will come up at the end as well. And there'll be a link to the video on there when BCS have finished redacting it to their satisfaction. Right, so anyone who doesn't know me, I graduated electronics from the University of Kent in 1973. I did an MSc in computer studies at Essex in 73, 74. Some people who I discovered afterwards were quite famous. And I was a research student for 4 years after that at Kent. I was also a part-time programmer. I wrote a number of compilers on various smaller systems. And then I was a lecturer and senior lecturer until 2015, mainly compilers and operating systems. And I managed or co-managed a number of different Kent systems, including an Elliott 4130, an ICL 2900 running VMEK, and then I was much more involved with running EMAS, which you've probably heard of before. And then a digital VAXcluster after that, running VMS. So, moving on. What is emulation? Well, I've talked about emulation before, but not in quite the same context as here. I was talking more about hardware before. So it's using one or more computers to pretend to be another computer. If anyone knows about the Church-Turing thesis, you can go and read that and you'll see more about it. And it could be a number of different levels, and I'm going to talk about that today. The aim is for the emulated system to be, or partial system, to be indistinguishable at that level from the real system. Both at the user level, so the user can look at something and not know they're not on a real system. At the program execution level, so you can have a program that you run and it will actually, again, not care that it's not on the real system. And then at the program level, where if you're writing programs, you can write them exactly the same way, and the emulated system is there. And there might not even be a real system, even in the educational context. Anyone come across the paper computer? No. Well, you can either do that with a sheet of paper, where you fill in boxes and cross things out and so on, and be registers, or you can do it with index cards and some boxes and so on. Is where I first saw it. There's a link in the website. So why would we want to use emulation? Well, there's more than one answer, of course. My reason mainly, I guess, is for fun. Emulating a computer I don't have, possibly couldn't afford, so you can play with one anyway. I would love to have a PDP-10, but PDP-10s, there's one actually up for sale at the moment, and I think the starting bid is 1.3 million, and it's in the States as well. It's come from the computer museum that got shut down. So I do that for interest and for nostalgic reasons, which are not games, but just programming, because actually the 10 is a really nice machine to program at the assembler level. Especially when it's got an instruction like jump, which is a no-op. If you want to actually jump, you have to say jump A, which is jump always. Things like that. But also people want to play games, and that's a very fruitful source of people using emulation. Then it's for education. If you want to know how a particular computer works, perhaps you'd like to learn about one. Perhaps for training, for perhaps a future job, you could get an emulator for a machine and go and learn how to use it. Because it's too expensive to buy, or perhaps your employer won't let you play with the computer because it's too critical, like it's running a nuclear power plant or something. And of course, you can use it for training people as well, in a nice context. So there's also for development purposes. Perhaps there are better debugging aids in the emulated machine. There usually are. You've got software. It's easy to add new debugging aids, which you couldn't easily do in the hardware. And a good example of that might be mobile phone applications, where you run Android on your PC or whatever. For selective replacement of hardware by software, and I'll come back to that. And for migration from legacy systems, perhaps you have a legacy system that you want to still use some of the code from, and you don't want to rewrite it. And again, I'll talk about that. So a whole series of things, really. More answers to why we do emulation. Software development before the real hardware has been developed. Particularly in the case of early mainframes, that was the case, but still now, you can emulate what you think you would like to build your computer for, give it to programmers and say, does this work? And try out new ideas and architecture you're planning, but you're not sure about. Interesting one is the regulatory context. You can have an emulator that's certified to be equivalent to the real machine. And if you get it certified, then you can run software that's been already certified on that hardware to run. And that, in certain critical contexts, that can be quite useful. For commercial purposes, an older architecture might be emulated to achieve backwards compatibility. And there are various ways of doing that. I mean, a simple one in hardware, of course, is the VAX, which actually a lot of the early VAX machines could run PDP-11 code. But in software, that's rather different. And there are levels, again, partial or complete. There's one example, which I'll talk about briefly later on. And also there is a link to another BCS video where somebody talked about this. There is some 50-year-old code running now for Fujitsu, which still exists in their modern system. But 50 years ago, it was running on hardware. Now it's running on emulated hardware, i.e. software, inside their new machines, because they don't want to actually update it. And of course, another one is playing old games, as I said. That's a really good thing. Speed is not generally an issue. You can. Modern machines are so fast that they're not going to give you a problem if you're emulating code. You might actually have a problem with the software still running too fast. There were cases in the early days of advanced hardware, like a 286 or a 386 PC, and you wanted to run a game and it wouldn't work properly. The classic one I remember is where there was a game where you had babies were being thrown out of a burning building and you were catching them on a sort of a fireman's type, trampoline type thing. And they were coming out so fast, they were bouncing off and splatting every time. And you couldn't get it to go slow enough to actually do it. So levels of emulation, as I said, complete or partial. And there's a spectrum there, it's not just those two. Because emulation is a complex business, and a lot of people don't realize how complex it is. They say, oh, I'll write an emulator over the weekend. It really isn't that simple. So you want to see exactly what you need. And you might not need to emulate at all. You might be able to do something which provides an API, which is enough for your programs when recompiled to run. But let's look at some ideas. Most of the emulators I've come across are open source. There are a few that are closed source, and obviously there are commercial products. Let's look first at the levels then, and complete emulation. This is where you literally do the whole computer system. This might be an older one, probably is. So you've got to emulate the CPU. You've got to imitate the entire instruction set. And you've only got to look at the specification of an instruction set to realize that actually it's a lot more complex than you think, because you've got things like setting condition codes and flags, side effects of instructions, all sorts of things. If you're trying to emulate certain microcodes, you actually have to simulate the pipelining too. There's memory. Well, that's easy enough. It's just an array, isn't it? But memory management. Okay, so you've got to start simulating paging systems, segmentation systems. You've got a peripheral subsystem at a high level, things like autonomous data transfer. You set up a control block and then say go, and it goes and does a whole load of stuff in the background. Then you've got peripheral controllers, which perhaps control a bank of disks or a cluster of tapes. And then individual things like the disks themselves, the console, the tape drives, printers, whatever. All of those things need emulation separately, and you have to think about what you're going to do there. So your computer program is first of all going to provide emulated memory. It's got to provide emulate this paging and segmentation, as I said, and this includes things like translated replicas like buffers, caches for the page tables or the segment tables or both. It's got to fetch instructions, decode them, and do the right thing. It's got to handle instructions and perform control and I/O. So an instruction perhaps writes to an I/O port, and that's got to go off and tell the emulated peripherals what to do. You might have memory mapped I/O, so you've got to handle part of the memory differently because that part is actually control registers for your peripherals. You've got to simulate interrupts. When a peripheral finishes doing something, somehow it's got to generate what looks like an interrupt in a real computer system. And that includes the clock, and the clock is a whole new problem. And lastly, you might have to provide things to replicate timing in the real machine. And timing can be critical. You can run test programs on the hardware which fail because the software is going too fast. There was a classic case here of the VAX emulator, which I'll talk about later, which was emulating a VAX which had some firmware in it, and they had permission to use all this firmware in the real in the emulated system. So they put the firmware into the emulated machine, and the firmware failed, saying this is wrong. This is going at the wrong speed. What they had to do is put something into the memory access, which slowed down access if it was accessing that part of memory, because it was a ROM and it was going slower. So there are lots of complications that you don't see at first. Another one about timing is there are certain tape drives produced by DEC which actually were very, very critical on timing. And if you didn't do things at the right time, or the interrupt didn't come at the right time, then it would say the tape had failed, and it hadn't. Emulation just of the CPU. You could do that. That's fairly easy to do. You can omit the parts that are done in other ways, so perhaps most of the peripheral stuff. But you'd have to do the CPU instruction set and the memory, perhaps the memory management, depending on the size of the machine. And the data input and output could be really simple. It could be something like pushing in data on switches, pulling it out on lights, or it could be a bit better than that. It just depends what you want to do. That would work okay. You can provide a single limited peripheral, and I've done this, where you just have some sort of linear I/O device, which you can pretend to be a paper tape reader or paper tape punch or something. It just produces a stream of bytes, which is, of course, what a file generally is anyway. So in that case, you've still got to construct your computer program. But here, you've still got to provide the emulated memory, the instruction fetch and decode, all the same, and perhaps handle some sort of minor peripheral. Well, that's all you have to do. Going up or down another level, you just have an emulation layer. Emulation of the instruction set with some memory. And this might be because there's legacy code you can't rewrite, and that code can be made to sit on top of a newer system. And as I said, that's been done with this 50-year-old code. Fujitsu had a system which they called VME when it was back in the ICL days. And ICL's VME system sort of survives because what they've done over the years is prune away some of the hardware-dependent parts of it and put it into software or into other hardware. They can now run VME on an x86 system, but the x86 system obviously doesn't support the instruction set of the ICL 2900, which it originally ran on. So what have they done? They put an emulator for the 2900 inside VME, and now that code can actually stay and doesn't have to be remade. And they've done that. There's a link to, as I said, there's another BCS branch going to talk on it, and I've done a couple of links. One takes you to the entire talk, and one to the relevant part about that. So have a look and see. So you're still going to provide emulated memory, but it's probably not very much memory because you're just running perhaps the code. And you're going to do the fetch and decode as usual. And you don't need to have any peripheral interaction except via the defined APIs. So that's fairly easy to do. So just going on to another part of emulation, we were just emulating very selective instructions. Computer manufacturers used to provide machines at several price points. It's quite common for you to buy a really basic machine and then have it upgraded at some point when your workload changed, you have more money, you have more need for it, and so on. And so top of the range machines would do everything in hardware. And cheaper machines emulated some of the complicated instructions. ICT rather did that with things like the 1900 series. Elliott did it with the 4100 series. IBM did it with their machines, and so on. Quite common. And the idea is that you have any instruction that you can't actually do directly because you don't have the hardware causes an interrupt. And the operating system takes over and emulates the instruction, no matter what it may be. And it was very common to provide machines, for example, that didn't have a floating point unit because they were expensive. And so you calculated the floating point in software. Decimal arithmetic as well, and some very complex instructions. In some cases, stupidly complex instructions, which you probably would never do these days. If you want the absolute definition of a complex instruction set computer, look at the VAX. The VAX had an instruction called poly, and it evaluated a polynomial to 31 levels, 31 levels of coefficient. And what you did was you gave the instruction all the coefficients and a single unknown variable, and it would then calculate the whole thing. So it's just ridiculous. The problem is that when they did it on the first machine, the VAX 780, they did it before the test programs had been written, and they did it before everyone had quite agreed on the spec. And the successive VAXes did it slightly different ways, and they never quite fixed that. And then, of course, there were the microcoded versions. There's at least 2 of those. The result was, in the end, they decided if they wanted consistency, the only way was to make all the VAXes cause an interrupt and do it in software. And that's what they did in the end. Again, there's a paper about that by one of the microcode writers, Bob Slipnick, and you can read that. It's on the website. Right, examples of emulators. I'm not going to do lots of them. A couple of closed source ones, but I'm not really talking about those. There's something called Win8, which is quite old now, but it emulates a PDP-8. And there's Caron, which is a PDP-11, and indeed other machines as well, like the Alpha AXP, the VAX, and so on. And that's a commercial product. And the idea is that you can run your legacy system on this instead of having the hardware. Open source, there are many. My favorite one is SimH, and you'll see why in a minute. PCJS, which runs in a browser. Hercules, which does an incredible job of IBM mainframes. DOSBox, which does an emulation of a DOS machine. And you may think, well, why would I want that? The number of games you can run on DOSBox is quite staggering, so it's quite popular. And what I haven't even touched on, because there isn't time in this lecture, is the collection done by the Computer Conservation Society. Now, they have done emulators for some really old systems, partial, complete, whatever. They've done the ICT 1900, for example. They've done some older ones as well. And rather than talk about those at length, I put a link there, and you can have a look at that. They're all, again, the link is on the website, or it should be. So there's a whole series of emulators there, so plenty to play with. I'm just going to take a couple of examples. One of them is Hercules. Hercules is, anybody use an IBM mainframe? Yeah. So this emulates System 370, ESA 390, and even the Z architecture now. So it's pretty well up to date, and it's just continually developed. And it runs under Linux and Windows and Solaris, FreeBSD, macOS, and probably other things as well. You really need a 64-bit machine for it. And there's a link there to Hercules itself. You can download it, and it supports lots of peripherals, 3370 terminals, console, printers, the old card reader and punch if you want that. Probably does paper tape as well. It does discs and it does tapes. Discs aren't always easy because some of the IBM discs are really weird. If anybody's ever come across CKD discs, you'll know what I mean. So that's rather nice and quite a good example. Another one is SimH, and SimH is something which I've used for many years. SimH stands for Simulator for Hobbyists. It's pretty solid. Bob Slipnick was an engineer for DEC, and he became a vice president. And most of the emulators he wrote were for DEC systems. But as we'll see later, this enabled other emulators to be written. So we've got all the PDPs, and I don't know how much you know about PDPs, but when Digital Equipment Corporation was started, about 1958, they asked their venture capital people, whatever they called them in those days, can we have some cash to make a computer? And I said, oh, no, IBM do that sort of thing, competitors, we can't do that, it won't work. And they said, well, can we build logic boards? And I said, well, yeah, that's all right. So a couple of years later, they said, look, we don't want to build a computer, we want to build a program data processor. And they got away with it. So they got money for a PDP-1. And the PDP-1 is an 18-bit computer, and there are very few of them left in the world now. And then we worked up through the PDP-4, PDP-7, then the 8, which is a 12-bit machine, the 9, the 10, which is a 36-bit machine, the 11, which is a 16-bit machine, and so on. And then they went on to build something much bigger, the virtual address extension, the VAXes. And there's emulators for 2 different VAXes there, an early one and a late one. There are some IBM ones written by other people using SimH. There's Interdata ones, as you can see, and the Honeywell 316 and 516. Anybody come across those? The 516 is actually more important in history than one might realise, because it was the basic interface processor for the IMP, as they called it, for the ARPANET, and therefore for the internet in the end. It's the machine that sat in between your mainframe and the network. And if you go to the Science Museum, you can see an exhibition there which has pieces from some of the mainframes, and also a control panel from a Honeywell 516, which you can inspect in the cupboard. That particular control panel, that actual control panel, that physical control panel, it used to be on a computer at the University of Kent, and I used it many times. They were actually quite surprised when I said, it's 44 years since I've touched this, when they allowed me to inspect it. It was actually that one. So there's classic SimH and there's other SimH, and I'll just sort of lay out the differences here, because it's a bit confusing. Bob Supnick have written SimH for years, and then a group of enthusiasts sort of said, well, we'd like to do more to it than Bob wants to. And Bob did pretty slow development and pretty basic stuff, making sure it all worked. And so this group produced what they called SimH version 4. Up to that point, Bob was still on an early version 3. And version 4 was pretty good. It's got lots of extra stuff in it. It can control hardware panels, it can do all sorts of things. And these enthusiasts weren't very organised, in my opinion, because you never got a proper release out of them. What you got was, well, this is how it is today, and there's another snapshot tomorrow, and another one. And so I never found I could take one and say, I know this is going to work. I can port this to another system and use it, because it'll be gone tomorrow. And so I never really got too involved in it. And this was done on GitHub. People would go on GitHub and modify it and push the stuff back. One of the major contributors, who I shan't name here, unilaterally modified part of it to do some stuff on the disk system. And he changed the license, which was basically the MIT license, to something which was no longer open source, which is a complete no-no, and a cautionary tale, because they had no proper governance, so there was really nobody to stop him. And what this meant was that he said that, well, yeah, from now on, you can't modify the software if it affects the disk subsystem in any way at all. And that is, I've locked it basically, and that's it. And I'll go after you if you do anything to it. That was by the 27th of May, and this was only 3 years ago, just over 3 years ago. Bob Supnick said, well, look, I don't endorse version 4 anymore, we can't do that. I'm only going to endorse classic SimH, which is version 3. And he would not recognise anything else. And who can blame him? That was completely against the whole ethos of open source and the rest of it. Bob would always let anybody do anything they want to it. So about 3 or 4 days later, the last revision of that SimH version 4, which didn't have that code in it, was taken away and forked and produced, and it's now called Open SimH. And another new group who set up a proper governance committee, including Bob himself, and so it's there. So you can. There's a bit about it on Wikipedia, not a lot, but it was. I remember it at the time. It was very bitter indeed. And so yes, if you're going to have any substantial open source project, you need to make sure that you've got proper governance for it, or nasty things can happen. So I've gone on about that a bit, but I think it's worth saying. Now, SimH also includes tools for doing things like creating emulating mag tapes. Essentially, they're blocks of bytes with head and tail on them, saying how big they are and things like that. And you need it both ways, because sometimes you want to actually wind tapes backwards and read them. Some hardware allows you to read tapes backwards. Cross-assembling, which is always quite good, particularly with smaller systems that can't support themselves assembling, that you might want to do that. Tools for access to the emulated disks. Usually this is at a higher level, this is at the level of the file system. So it'll take an image of a disk from, say, a Unix system and allow you to read files of it, which is quite good. And there are a massive number of software kits available for use on the emulators. And generally speaking, these have got licenses which are fairly permissive. So you've got Unix 6th edition, the famous one that I started using 50 years ago next month. Ooh. For the PDP-11, BSD Unix for the VAX, Mini Unix. Anybody come across Mini Unix? Not Minix, Mini Unix. It's basically a single user sort of Unix running on a non-memory map PDP-11. So it's quite interesting. It's a very different system. TSS-8. The PDP-8 had an operating system called OS-8 from about 1970 onwards, so 5 years after it came out. And that was a disk operating system. And if you look at OS-8, and you can obviously go and get the emulator and build it and run it, OS-8 is remarkably familiar because they've decided on having two-part file names with a dot in between the two bits. They decided to have command options, which were a slash followed by a single letter. They had device names, which were a name followed by a colon. Where have we seen this before? This got picked up by CPM and obviously by Microsoft and so on. So TSS-8 was different. Now, bearing in mind that the PDP-8 maximum memory is normally 32K 12-bit words. It's not a big machine. It wasn't a very fast machine either. But they did a time-sharing system for it, and you could have up to 8 users, and you can compile and run small Fortran programs, which is really nice. It was done actually as a project by some of the employees, almost in their spare time, then picked up as a product. And they decided to brand it TSS-8 because they were taking the piss out of IBM. IBM had something called TSS 360, which was a proper time-sharing system for the 360. And to produce TSS-8 on that and actually make it work was really embarrassing, I think. So good fun. And then they got older stuff like autocoder and Fortran for the IBM 1401, which is going back much further. So SimH has got a hell of a lot going for it. And it's all free, of course, and open source. It's in C. But the most important point about SimH probably is that it's a framework. If you want to write a new emulator, SimH will do a lot of the work for you. So as long as you know your machine fairly well, you can write an emulator for it. So I'm now going to talk about something slightly different, and you will have seen a little bit of this before if you've been coming for years. Hardware refinements. Enthusiasts have always tried to add pretty lights and things to these things because we like pretty lights. One of the wonderful things about our ICL mainframe was the sheer number of pretty lights it had. And the emulator is generally, in these cases, hosted on a Raspberry Pi because they're cheap, relatively speaking, and you incorporate that into the panel. So you get network connectivity, you can access it via Wi-Fi even. And there are various hardware enhancements, lots of them. But the most well-known ones, I think, are probably the ones from this guy who styles his site Obsolescence Guaranteed. And there's the link, again, on the website. And they're kits, and you can sometimes purchase them pre-built. I know somebody said, well, my site's going, he's not much older than me, he said, but I'm going to buy the pre-built kit. They've got 3 there, which are the PyDP-8, PyDP-10 and PyDP-11. And soon they're doing a PyDP1, which will be quite interesting. So I'm saving my pennies for that. These are open source hardware as well, so you can get all the details from him if you want to build one of your own from scratch. And anyone who's used the original machines would find them very familiar. So here's a PyDP8. This is his first attempt at producing a kit. And he had a couple of problems. One is that the front panel was meant to be a push fit, and it wasn't really very good push fit. So you can probably see on the right-hand side, so about there, it's a screw to hold it in. The box is actually not a pre-built case. It's a kitchen storage box from Amazon, which is good because I drilled some holes in mine and then changed my mind, so I bought another one off Amazon. They're very cheap. So that's PyDP8, and as you can see, it's got all the nice stuff on it. It's got Wi-Fi. All you need to do is plug in some power, and you're ready to go. And you can run OS8 on it and do things like that, and TSS8 as well. It has 26 switches and 89 LEDs, because that's what computers had in those days. So you can see all sorts of data buses inside. They're being sampled, obviously, inside the Raspberry Pi, but it works pretty well. And it even shows you the instruction it's executing for a single step in it. Now there's a PyDP11. Some of you must use PDP11s. Yeah? Yes. So this is basically an 1170 panel. It's one of the nice ones. After that, DEC started going for very boring panels, which had if you were lucky, had a few keys to press and a small LCD. If you were very unlucky and you bought the cheap version, you didn't even get that. You just got a few switches, and it prompted you on the console. Very boring. So the PyDP11 runs well, 16-byte, but it's actually 16-bit machine, but it's got address extensions, which are why the address part has got more than 16 bits on it. So you can run quite big things. I think it's either 128 or 256K. So big bytes, and that's quite big for a PDP11. And that required 30 switches and 84 LEDs. So not quite as many LEDs. But as you can see, it looks very nice. We've got the knobs to select various displays and things like that. And it's pretty good. Needless to say, I've got one of each. Then they decided to do a PyDP10, and this has taken some years because of lockdown and various other things. But it did arrive last year, and I built mine, and it works. And the PyDP10 is that. Now, you have to know that the PDP10 went through 3 major versions. And the first one was the KA10, which is the one that I used in real life. And the KA10 console looks like that. That's just the console. You've got an entire room full of machine because it's actually a mainframe. It's a 36-bit mainframe. It's a serious machine. And so this is just a 60% size scale model of the actual console. And as you can see, all the switches are properly color-coded and everything else. And it's got everything you want. It's the only real DEC mainframe that there ever was. It's got 74 switches and 126 LEDs. Get quite tired soldering those. And testing them afterwards as well. It's got serial ports, it's got a debug port, and it's going to have a maintenance panel on the back. They're now producing a maintenance panel kit, quite a small one that fits on one end, and that's a replica of the original maintenance panel, and now you can do some clever things. And the kit takes about 6 hours to build for that one. It took me a bit longer because I was being very careful. I'd made some screw-ups on previous ones. But just to give you an idea what the kit looks like, that's it. So what you have there is my power supply at the back, which has nothing to do with it. It's an injection molded panel with 2 pieces, some of it's black, and 2 separate circuit boards, one for the switches and one for the back panel. Various other pieces to fit on the back, and obviously other things like the front panel and so on. So it's quite a nice arrangement. Off to the left at the back, you can see a bag of 126 LEDs. And to the front, just the corner bit showing is a bag of 70 odd switches. So put that together and you've got a very nice little machine, a big machine there. And of course it's faster than all the real PDP-10s, so much faster. I've got that running on a Raspberry Pi 5. And I want to talk a little bit about how emulation actually can be implemented. I'll do this in two stages. First bit is looking at the PDP-8. It's one of my favourite machines, dream about it almost. It's got a 12-bit word, there are no bytes, too early for that. 32K words, one register called AC, a program counter saying where you are, and a single bit called the link, and also an optional register called MQ, which is memory quotient, which could extend the AC if you want to do some things more than 12 bits. It's got some internal registers you have to know about for memory management. And it has 8 opcodes. It's got a 3-bit opcode field. So only 8 opcodes in the entire machine. So the first one is TAD, which is 2's complement add, and it adds whatever's in memory at that address to the accumulator. DCA is deposit and clear accumulator. And that's why you don't need a load instruction, because the accumulator is 0 after you've stored it. Increment and skip if 0, which does that to a memory location and skips the next instruction if it becomes 0 for counting. Logical bitwise AND, jump, and jump subroutine, which leaves a return link somewhere. 7th instruction is IoT, which is got a 9-bit address field, which is used to address various peripherals, and also part of it to run memory management and things like that. And lastly, you've got what are called the operating instructions, which are basically 9 bits again, encoding conditional skips and shifts and things like clear the accumulator. There are clever ones like clear accumulator, another one's increment accumulator. And the bits are arranged in such a way that you can do both in the same instruction. So to load one into the accumulator, you execute clear accumulator, increment accumulator with the opcodes all together. Very, very clever design. If you want to know more, Wikipedia again has got something there, and there are lots of other places. I've listed some of those on the website. Now, to emulate the PDP-8, all you need really is 32,768 cells, which are going to be in 12-bit words, at least 12 bits in width, cells for those internal registers and the external ones, and a Boolean flag for interrupts. You need a user interface for setting up where you're going to start and for getting stuff into the memory. And the emulation itself is this pseudocode here. Set something called halting to false, and then until that comes true, you extract the instruction, decode it, fetch it, execute it. If it's the halt instruction, you set that, and then increment the PC if necessary. So it's a very, very simple idea in theory, but of course, extracting instruction and decoding it and executing the instruction are the hard bits. And that's not even going near peripherals or memory management. Okay, so if you want to use SimEdge to write a simulator, an emulator, you can do that. There's complete documentation. I've just done the front of it there. There is a document which Bob Subnik wrote, and I did update back about 6 years ago because there wasn't everything there. When I started writing a particular simulator, I found some queries, and Bob Subnik was incredibly good with me, and he patiently took me through what you have to do and what this meant. And then I clarified the documentation, added new bits. So that's available. So to prepare it, first of all, you need to decide how you're going to map data types. You may need 64-bit variables. Say you're emulating a 32-bit machine. It's still easier to use 64-bit variables because it's easier to detect things like overflow and instructions and things like that. Integer size on the actual thing, what you're going to use. What's going to be the default number base? On the PDPs, it was generally octal. On the VAXs, it's hex. On other machines, it's also hex. So you need to know that so you can actually have sensible and reasonable things to the user. Decide what devices you want to implement and not get too ambitious to start with. So you need a keyboard, you need a display, of course, of some sort, really just a teleprinter, disks and tapes, and they're all devices. And there are other pseudo devices as well that you'll come across, like non-volatile RAM, for example. And there might be multiple instances of some of those, and some might even have multiple controllers. You only have 8 disks on the controller, and you want 16 controllers. It's nice to provide a binary loader dumper, because then you can freeze it, dump it, and then come back later and carry on where you left off, which is quite useful. you're meant to provide functions for parsing and printing symbolic instructions. In other words, you basically got to write a mini assembler. It can be quite a simple one with some very basic syntax, but you need that because when you're testing, you often want to just key a few instructions in and try them out. You need to provide functions to emulate the peripherals, and they get hooked into the device table. So when you do something in the simulator that requires access to a device, it dives off into the device code. And optionally, you probably want to provide things for parsing and printing addresses, because the addresses are again, dependent on the machine, how you show those. Some of them, for example, might show us as a 2-path address in a different base, I don't know. An extension table for extra user commands. And I've added extra user commands, and you've got to provide a command input function, obviously, but just to get the commands in. The sort of additional commands I've had are things like set commands. Good example is a machine I'm doing an emulator for now, which has an idle instruction. And if you've used the PDP-11, you'll know about the wait instruction. Similar things, basically wait for an interrupt before you carry on. And the idle instruction is fine, but for debugging purposes, it'd be nice if that were actually treated as a halt instruction, so that we can stop at that point, because there is no halt instruction. And so you can actually, I have a set command which allows me to set the behavior of that instruction. Then you've got a rather interesting problem, which is the time base. How do we determine machine time? It could be microseconds if you put in a timer, but usually what people do is put an instruction counter in, and that's good enough. So you tick up 1 every time you execute an instruction. You could provide a way of organizing interrupts, and the easiest way there is that the peripheral will set a flag, perhaps more than 1 flag, and that might be propagated up through a controller code. And after every instruction is emulated, the CPU emulation will check to see if an interrupt flag is set. And if so, then the code will dive off into the interrupt handler. And of course, you may have multiple sources of interrupts. So again, that becomes more complicated. You've got to feed them to the right vector and so on. And then you've got your fetch and execute instruction loop, of course. And you've got to provide that. What SimH does is provide all the stuff that wraps around it. And you just provide this inner function, which is the execution module, and then hook everything off that. So that's how you write one, really. Emulation of devices, let's go into that a bit more. Including some of the pseudo devices, is all done via the device table. The device table will have a series of entries in a well-defined format. So one will be to initialize the device, another will be to reset it, another one to do input-output on it, another one to control, and so on. And you may, as I said earlier, you may have to have real-world timing. If the device responds too quickly, you may actually uncover a bug in the operating system. It's got a race condition they've never come across before because it's not supposed to respond that fast. And you could also have a sanity check in the operating system, like the one in the VAX, wrong. And we're probably going to link your devices to files. Paper tapes, if you want to do all punch paper tapes, pretty easy. You just have a linear array of bytes in a file. Tapes will have some sort of structure to the file, but it'll basically the same thing to emulate each block. You have an interesting one with things like deck tapes, which are actually not really ordinary tapes. If anyone's come across deck tapes, they're essentially a linear disk. They have numbered blocks. They're all the same size, and you can jump to any block you want and just tell the hardware, I want to read block 57, and it will wind to block 57 and read it with minimal code. And disks are a whole new problem because I think I mentioned earlier, IBM CKD devices, they are not simple disks. They are disks which have variable size sectors, even on the same track if you want, which gets very, very silly. They have headers. And SimH actually has to provide some help here. Again, it's a framework. So it will provide you with access to serial ports, serial multiplexers, network interfaces even, which map to your real network, and things like magnetic tapes, which are going to be emulated, but which will provide you with all the base stuff for. Clocks, the actual clock in the machine, I think I mentioned internal clock will probably be the time base, but then you've got a real-time clock as well. Time on the wall. We're doing all right for time on the wall, yeah. Time on the wall, I've got that linked into the actual host system's clock, so it actually reflects the right, it translates the numbers, so it gives you the right things. I mentioned idling as well. If you're idling, it will consume significant resources quite often. It's basically in a tight loop waiting to do something. So you may want to offload that, and there are various ways of doing that. Some SimH implementations actually look for what they know is the idle loop in a particular operating system. And when they see it, then they will suspend or do a long sleep. So SimH for the VAX has actually got at least two different modes of operation. There's a VAX VMS operation and there's a NetBSD operation. And they're looking for a different idle loop, idle state set of instructions. If you've got nano sleep facilities, which most modern, say, Unix-like systems do, you can use that as well to cut down the load. Here's just three screens which just show you a demo just to finish off. This is the VAX simulator, and you probably want to go and read this offline. But at the top there is my command prompt from a machine called Rapture, and I just type VAX. The simulator starts up, and I've asked it to show me all the devices. It's got a whole pile of devices. It's got ROM and non-volatile RAM and a clock and terminals and all sorts of things, printer, loads of different disks and tapes and so on. And then it comes back to the simulator prompt. And I'll go on to the next part of it, which I say boot CPU. Now you might say, why don't you say boot device? And the reason is that the VAX is rather odd. It has this piece of firmware, which I mentioned earlier. What you're actually booting is that, so it can do all its setup. So there it is. That's the firmware doing a whole series of tests, counting down from 40, and eventually it completes the tests. And because we have all this timing fiddling in there, it actually works. And then I just say boot, and it boots off the default device, which is DUA0. And what you're seeing there is the actual startup of a VAX VMS system, which I was running yesterday. And it says copyright Compact, because Compact took over DEC. And then, of course, HPE took over Compact and completely killed it. So that's the startup. Now, all those messages in the bottom half of the screen there are basically messages from the operator device, and they go on for pages as per usual. So I've skipped those. The last bit is it's finishing that, and it says we're starting the network. It creates some processes, and then it logs itself out. We're now ready to log in. So that's a proper VAX VMS system running on my PC last night, or yesterday afternoon. So it's quite nice to do. Now, two last small things. Hercules is still being developed because IBM are still developing their mainframes. And emulation of the x86 is obviously still going on as well. I'm working on an open source emulator for the ICL new range systems, the Peace series, which are the earlier series machines, because I know more about those. And there's a picture of a Peace series system at ICL many years ago. It's called Risley. So you can see it's that sort of level of things. I'm emulating the two screens on the operating console and a row of disks and some tape drives on the left there. And what you're seeing in the back, those tool cabinets are CPU, memory, disk controllers, and so on. So, if you want to do this, obviously you can go and buy one of these kits. The problem with the kits is that they're not incredibly cheap, and obviously if you're not into electronics, they're a bit of work as well. What you can do instead, of course, is use any PC for the job. Wouldn't it be nice to have a portable mainframe? Something that isn't terribly big. So here is a portable mainframe. Banana for scale. It's called a PI Man 5. And the kit's about £60, I think. And then you put a Raspberry Pi in it. And the great advantage of the PI Man 5 is that it's got 3 fans in it, including one massive one. And given that Raspberry Pis tend to go hotter and hotter, the Raspberry Pi 5 you really can't run without proper fans. So, and it's also got lots of pretty lights that can be made to shimmer and all the rest of it. So that's just good fun as well. And it's got transparent sides, as you can see. It's got USB ports. It's got 2 HDMI ports, and it just runs off a 5-volt supply. So you can buy those. And the PI mouthful is quite nice. Here's the kit before you build it. It's all very, very nicely put together. The brown bits are the acrylic before it's had the protective coating taken off. And top left, you can see what powers it all, which is the Raspberry Pi. The next to that are 2 fans, and next to that, up towards the right, is that strange thing there is actually a very, very large fan, and a heatsink that sits on top of the Raspberry Pi. So, and it even gives you the tools, the screwdriver and spanner that you need. So it's quite nice. So just to finish off, playing with old computers is obviously instructive and fun if you're into that sort of thing. But real old computers are hard to obtain, so you don't do that. You can run SimH. You can just go off and download SimH and be running VAXVMS later tonight if you were really sad. Emulation with the display hardware like the PiDPs is nice as well, but that's obviously more expensive. But it's instructive, I think, and fun for some value of fun, obviously, if you want to do this. I recommend it if you have some spare time. So I'll ask for questions, there's the website, but I'll leave the following slide up, which is contact details and the emulation website. So, anyone got any questions? Quite pleased with that timing. Yes.
Well, what kind of software engineering skills do you really need in order that you can start actually building an emulator?
Need to be a reasonably competent
programmer. I ask that in a
all.
modern context.
Yeah.
Most people probably learn how to program in, I don't know, JavaScript, Rust, or something like that.
Well, I mean, I've always said to students, if you can program in one language, you can very quickly pick up another. If you know Java, for example, you're going to get C with no trouble at all. And I don't think that would be a great problem. I have to say that not all of the SimH code is the most transparent C I've ever seen. But actually, you don't really need to look at their code much. That's the point. It's just specified for you. And of course, you can go and look at the examples. There are lots of examples of all the other emulators because they're all open source, and you can go off and do them. So I should say, by the way, that my emulators actually run on the classic SimH because it's not a moving target. And the guy who did the HP simulators pulled them back from version 4 and decided to use classic SimH because he got fed up with the moving target too. And he and I correspond quite a bit because he pushes it out to various systems and I do the port for FreeBSD for him. So, but it's not too bad. I mean, a competent programmer who can pick up a new language if you don't know C. Anyone else? No, I've stunned you all. Well, the timing seems to be all right. I'm going to go and get a cup of tea now, or coffee. So feel free to hang around and chat. And I hope you enjoyed that. The website has got everything on it except for the video, because I'm still speaking. But it will actually contain that, and the BCS have done what they need to do and made sure I haven't invaded any copyright. I did actually have one of my lectures had one image taken out of it. It was a picture of Colombo. Thank you.
Thank you.